Hi, my name is Laura Meredith. I'm a grad student in the Earth Atmospheric Planetary Science Department at MIT, and we're here today at my field site. This is Harvard Forest in central Massachusetts, and I have an instrument out here. It's been running for about a year. So this is the main Ems Tower, 29 meters tall, and we unlock this little bottom section here to actually climb the tower. Which you do by wearing a full body harness and hooking yourself onto the static line with an ascender, and then you just make your way up the rungs. And so with my instrument, I sample from 2 points on this tower, and they're both above the canopy. So I have two gas inlets, 2 temperature shields, and then I'm using data from the sonic anemometer, which measures wind in all 3 directions. And so the purpose is to measure a gradient of hydrogen and of temperature, and from that we can calculate the flux of hydrogen either in or out of that canopy space. And there are a lot of other inlets up there, I guess. And so in addition to this main tall tower, I wanted to set up a gradient set that's below the canopy, that's closer to the soils, which is where hydrogen is being consumed. And so I set up this small tower. Now on this tower, an inlet that's about 0.5 meter off the ground, and another that's 3.5 meters off the ground with a sonic anemometer in the middle. And it's been really interesting to see the gradient of hydrogen concentrations all the way from really close to the surface to above the canopy. And because of the strong soil sink, we see really strong gradients established. So the microorganisms are very actively working on the air that's close to the soil, and especially in nighttime periods when the air is very still and there's not a lot of mixing that occurs that would erase those gradients. We see the gradients just get stronger and stronger, and see differences of 1/3 less hydrogen near the soil than up above the canopy, so just over about 100 feet, which is a pretty strong gradient. And one interesting study that we're doing here is to understand how gases like hydrogen and also carbon dioxide and carbonyl sulfide are moving through the snowpack. So how strong of an exchange these gases continue to have even when the soils are covered with snow. And it's interesting because you would think when soils are covered with snow, there's exchange maybe gets cut off, but snow is a very porous medium that allows gas to diffuse through its matrix, and snow actually really protects the microbial community that's under the snow. The soil microbial community is insulated from air temperatures, which can be far, far below zero, and microorganisms will work pretty effectively down to maybe -4°C, but they're not very happy a lot further. So the snow actually keeps the soils above freezing for most of the year. And so when we're interested in things like global change, and we're expecting changes in snowpack, warmer temperatures might mean less snowpack, might mean more snowpack, but in either case, snowpack may actually be protecting microorganisms and continuing this gas exchange in a way that we wouldn't think about intuitively. So it's interesting to study that. And we're doing that with the gas measurements themselves. Carbonyl sulfides measured by a postdoc at Harvard named Regine Komane, and then I'm measuring carbon dioxide fluxes and hydrogen. And then we have these snow stakes out here around this small site, kind of look like little candy canes. And Josh McLaren of Harvard, he set these up, and he's got a camera up on the tower over here that is looking down on the snow stakes and looking down on this general area. And so with the camera, he's recording images every half an hour and using the amount of visible snow stripes to tell us how deep the snow is, and then also using an algorithm with the image to compute what the snow % area cover is. So we have those data and some information about how heavy the snowpack is to tell us about snow extent, depth, porosity, and then we have the gas measurements, so we're hoping to tell a really complete story. All right, so this is the instrument that I have put together. It's basically composed of a lot of different components from many different sources, but the concept is pretty simple. So I bring in air. So air is pumped in through this hole in the wall from the inlets that we saw in the tower. So they range in heights from 0.5 meter to 29 meters well above the canopy. So the air samples are brought in, and then they're brought into these big glass volumes, and I'm just mixing up air because it takes me 4 minutes at least to make one measurement to measure hydrogen once. It takes me 4 minutes, and so I use these volumes to physically average the air so that I want to compare air from one 4-minute measurement to air from a different 4-minute measurement. So I just average them for 8 minutes by mixing for 8 minutes. And that's how I make sure that I'm comparing the right air samples. So I bring in all this air, and then these are all just valves that allow me to select one height from the tower at a time. And half of the air is sent through this Medusa-looking valve to the gas chromatograph, which is where I measure hydrogen. And then the other half is sent down some tubes to this lower instrument where carbon dioxide is measured. And then everything else you see here are just, these are the computers that I'm using, controlling devices for the electronics, the valves, the data loggers, all that kind of stuff. So this part I call the front end. This is just where I select the different streams of gas, of air that are coming off the tower, and I send them to the main instruments. And so these here are the main instruments. And this top one here, so this is a gas chromatograph. And the whole concept of a gas chromatograph is that you have a sample of air, and then you shoot that air into a column, and you have a carrier gas. So in my case it's helium, so it's like a river of gas that's sweeping this air sample through these columns, which are wrapped around and around and around. And different components of the air, so different molecules, move at different speeds through that column. And hydrogen is a really fast-moving small gas. So H2 moves incredibly quickly through the columns and is separated from the other gases like oxygen, nitrogen, like race cars on a track. So they just keep getting separated. And I only let hydrogen come through to the end of the column, where there's a detector. And so I use this detector here. It's called a Helium ionization detector, and it can basically detect anything. And so I send my hydrogen that's been separated from air to that detector, and I measure how much hydrogen there is in the air sample that started at some height on the tower. So this is how I measure hydrogen every 4 minutes. And then below is an instrument rack that was designed by Bruce Dowby at Harvard. And this has been used for a different study, and we're also just making use of it here. And it has 2 instruments that analyze carbon dioxide. And that's done by measuring how strongly carbon dioxide, or how strong the absorption of IR, of infrared light, is by carbon dioxide at a certain wavelength. That we know carbon dioxide absorbs very strongly at. So the more carbon dioxide, the more strongly that light is absorbed and attenuated, and the less light you measure. So that's how that instrument operates. And so basically it's just running 24/7 out here. I'm sampling. I go from the top of the tower down and measure at each height, and then I have a lot of data processing to do to then calculate how strong the flux of hydrogen is into the soils, how strong carbon dioxide is coming out of the soils, and understand the actual ecosystem and what's going on. Okay, so here we have 2 plots, which is sort of what I see very consistently from the system, and what it tells me about the ecosystem is what I'm going to explain. So the top graph is showing area, which I'll explain later, and the bottom graph is showing detector response. So this is for the hydrogen measurements, and what you see on the x-axis is time, and the y-axis is detector response. So as time goes along, nothing's happening at the detector. It's just a constant stream of carrier gas, a background level, and then as that separated clump of gas hits the detector responds in proportion to how much gas there is. And so you see a slug of neon hits the detector, and directly after is hydrogen. And the detector will respond to how much is there. So what you can do is you integrate the area to get the area under that curve. So you have a peak area, and that's proportional to how much of that particular gas there was in the original air sample. So then this top graph here is showing those areas. So each plus sign is one measurement. This was made in 4 minutes time, and what you see is that there are higher concentrations or larger peak areas above the canopy than below, and that's because of the soil sink that's below the canopy. So this the green pluses that are samples of air that are just half a meter off the ground have much less hydrogen than the samples that were 3.5 meters off the ground, which have less hydrogen than the ones at the top of the canopy. So this gradient is really apparent in the measurements, and we see cycles that change throughout the day, that change depending on temperature, and those are the things that we want to understand are what causes larger gradients to be observed, what causes larger fluxes of hydrogen from the atmosphere into the soils. So that's basically the concept of gas chromatography used here.